Okay, so we're going to continue working with our conditional probability and our tables, and we're also going to work a little on some tree diagrams here. And so we have our first problem, media usage and good grades. So in January 2010, the Kaiser Family Foundation released a study about the influence of media in the lives of young people ages 8 to 18. Now, in the study, they found 17% of youth were classified as light media users. 62% were classified as moderate media users, and 21% were classified as heavy media users. Then of the light users who responded, 74% described their grades as good, meaning A's or B's, while only 68% of the moderate users described their grades as good, and 52% of the heavy users described their grades as good. Now, according to this study, what percentage of young people ages 8 to 18 describe their grades as good? So we're breaking this down using our 4-step process. And this is something that you'll see a lot more second semester, and it'll seem a lot more clear on how you break it down. But the main idea is what are you trying to find? So you've read the question, do you understand what you're looking for? And so can you state that? So when you get to the very end of the problem, you can state, this is what this means, because you can go right back to that state process and say, this is my answer. So our state is what we're trying to find, and that is what percent of young people describe their grades as good. Now, for the plan, we're going to go ahead and talk about what do we already know. So we know that light users are 17%, so 0.17. Moderate users, 0.62. Heavy users, 0.21. Now, the rest of it's a little weird, because they say, of the light users, 74% had good grades. And so this is a conditional probability. The probability that they have good grades given they're a light user. We knew they were light users, and 74% of those had good grades. So that is a conditional probability right there. And then the probability of good grades given moderate user, 0.68, and the probability of good grades given heavy user is 0.52. And we want to find the probability of just good grades. So we can do this 2 ways. We can do this with a tree diagram, which is important to know because tree diagrams are one of the standards that they test on the AP exam. Plus, it's really good for as we get into chapter 6 and we start talking about multiple things happening. Tree diagrams are really good for that because two-way tables, which we prefer to use, at least I do, only looks at 2 different variables happening or 2 different events. If we start looking at 5 events, we can't really do that in a 2-way table. So tree diagram is another thing to look at. And it's nice using a tree diagram with smaller amount of events because they're easier to draw. So I'm gonna show you the answer using a tree diagram, and then I'm gonna use the 2-way table and kind of relate the two so you can see how that is. So our first event they talk about is media usage. So we have a light, a moderate, and a heavy. So I'm going to go ahead and break up our first as a light user, a moderate user, and a heavy user of media. Now our light users are 17%, so I write my percentage on that little line, my 62%, and my 21%. And the reason why we write our percentages as proportions is because if we mathematically have to do anything with it, we have to do it in proportion form. So what we're going to do now is we're going to go ahead and break this down based on the conditions. So my light users then were broken up into good grades and not good grades. So 74% of those light users had good grades, which means then 26% did not have good grades. And then I can break it down over here. Good grades, not good grades. So in my moderate users, we had 68% had good grades, which means 32% did not have good grades. And then I can go to good grades and not good grades for heavy users. So for my heavy users, 52% had good grades, which means 48% did not. And so those are those conditional probabilities. Now, so now that we have those conditional probabilities, we actually have the ability to calculate the probability of and. So at this point, the probability of being a light user and good grades, I would actually multiply these out. So 74% of the 17% will tell me this probability. So I'm going to go ahead and move this up a little. And so this is going to give me 0.158. And I could keep doing that as I move down. But the idea is I want the probability of only good grades. So I'm going to do only the ones that have good grades. So the probability of M and G would be 0.4216. The probability of H and G, H and G is 0.1092. So when I want only the good grades, these are like the individual pieces from our table. And so I can go ahead and just add all these up. 0.1258 plus 0.4216 plus 0.1092. And I get 0.6566, which is about 66%. So what I want to talk about now is how do we put this in a table? What is our other option? And so we could look at our table as we have light, medium, and heavy users. And then we have the option of good grades and not good grades. And so of my light users, 17% were light users, medium users, 62%, heavy users, 0.21%, and then 74% of my 17 are here. So then I would go ahead and times that out, and I'd get the 0.1258. And then I could multiply again. My 68% times the 0.62 gets the 0.4216. So the same idea, just a different way of displaying this data. And then you can add them all up, 0.6566. And then if you wanted to fill in the rest of the table, we could actually go ahead and do the 0.17 minus this to get this value. Or you could do the remaining percent, 0.26 times the 0.17, and that will tell us our value. And so, again, different ways to solve it, different ways visually, but all gives you the same answer. Okay, so now we're going to look at our next problem. And this next problem kind of foreshadows what we're going to be looking at in Chapter 6. So we have a first trimester screen, which is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine in November 2005, approximately 5% of normal pregnancies will receive a positive result. Among 100 women with normal pregnancies, what is the probability there will be at least one positive result? Now I have some words scratched out there because it says false positive, but for some reason the false is not supposed to be in there. Okay, so again, our 4-step process, going through our state, what are we trying to find? If 100 women with normal pregnancies are tested with this screen, what is the probability at least one woman will receive a positive result? Our plan is, it is reasonable to assume that the test results for different women are independent. Why do we need to state this? Because the method we're going to use has to deal with the independence rule. So does one woman's test result affect another woman's test result? And that is reasonable to assume that one woman's test result should not affect another woman's test result. So, but you have to really think about the problem because sometimes it's not reasonable to assume independence. To find the probability of at least one positive result, we can use the complement rule and find the probability that none of the women will receive a positive result. The reason why we would do this is because, in other words, we have to look at all the different possibilities. And if we're looking at 100 women for one positive result, imagine the tree diagram that we would have. So this is for one woman, positive, negative. For two women, positive, negative, positive, negative. Can you imagine doing this? So that way we've got 100 different events in that tree diagram, so we could figure out how many different ways we could have at least one positive. Well, luckily, because my only other option rather than at least one positive, so looking at all the one positives, or all the two positives, or all the three positives, and so on and so forth, instead of looking at all those probabilities and adding those up, I could look at what I don't have, or what I don't want, which is no positives. And since there's only one case of no positives, I can use the complement rule to figure out all the remaining probability. So what I do know is that the probability of a positive is 0.05 because I have that 5%. The probability of negative then is 0.95. The probability that all 100 are negative. So the probability of the first one is negative, 0.95. The second one is negative, 0.95. The third one is negative, 0.95. And so on and so forth. So really, I end up with 0.95 for all of the 100. So I can calculate that, 0.95 to the 100th power. So on my calculator, I'm going to do 0.95 to the 100th power. And this gives me 0.0059205292. Now, I want the probability that at least one is positive. So I really want the complement. So I'm going to subtract this from 1. And that should tell me my value. And I'll go ahead and round this one, 0.994. So really high percentage. There is over a 99% probability that at least one of the 100 women with normal pregnancies will receive a positive on the first trimester screen. So the one question I have is, well, why isn't it just 95%? Well, it's 95% chance for that one person, but then you have to look at all the different combinations that you could get. And so that kind of leads into the idea of how many combinations are there? And then how big is that sample space? What are all the possibilities? And that sample space is so huge that we wouldn't even want to write that out. And so we have mathematical ways to work with that. And so what we'll find in chapter 6 is we actually work with the probability idea of a combination. How many different combinations, and then what's the probability for these combinations? Because there's not only one way to have one positive person out of 100. The first person can have a positive, or the second person can have a positive, or the third person can have a positive. So there's 100 different ways to have just one positive. Well, how many different ways are there to have 2 positives, and 3 positives, and 4 positives? And so we've got to be able to have a mathematical way of figuring that out. And that's what we're going to talk about in chapter 6. Okay, so just to remind you, calculating conditional probabilities, the probability of A given B is the probability of A and B. Over the probability of B. And so then we actually have this ability to, with conditional probability, I can actually go ahead and manipulate this formula. I can times by probability of B on both sides, and I get another formula that we have, that the probability of A and B is really the probability of B times the probability of A given B. Now, if they're independent, our rule is this is the exact same thing as the probability of A. If they are not independent, then I take this conditional probability and I times it by the probability of B. So the relationship between these ideas can be very complicated. Luckily, we are given formulas like this on our formula sheet to help us remember. So our last question in our notes, we classified U.S. households according to the type of phones they used: cell phone or no cell phone, landline, no landline. What is the probability that a selected household with a landline also has a cell phone? So the probability that a randomly selected household with a landline, so we're given that they have a landline, what's the probability that they have a cell phone? So this is a probability cell phone given landline. So I know they have a landline, so I get rid of no landline. And what's the probability that they have a cell phone? So here's my cell phone out of my total landline. And we talked about this in class the other day, but it's a good idea to have this in your notes just to remind you. Which is about a 77% chance that a landline user also has a cell phone. Okay, so that's it for chapter 5. Be prepared to get your practice test. Remember, out of all the things that you do, your practice test is probably the most important because it gives you very similar problems to what you're going to see on the test.